Let's continue our look-see at the Proxxon FF230. That stands in German for Feinfräse, which means fine milling machine. This is one tiny little milling machine. This is the second part of a video series I started a really long time ago, and apologies if you've been waiting for the second part. My work-life balance became quite imbalanced. But I'm back now, and well, here's a video. In the first video, I looked at the table, which I thought was really quite nice. And in this video, we're going to turn our attention to the Z-axis, which is, well, it's a bit more of a mixed bag. In this video, what I'd like to do is start off with the externals. We'll go over the controls, what they do, a little bit of usage notes about how you use this machine. In the second part of the video, I'm going to tear down the Z-axis. It's been a while since I've done that, and I'd be curious as to whether any swarf is being building up into places where it really shouldn't be building up. And then in the third part of the video, I got some test equipment, and what I'd like to do is get a little bit of a handle, a little bit of a measure on just what sort of play is in the Z-axis, and perhaps come up with some ideation on how things could be potentially improved. Anyways, let's get going. Z is not dead. Let's start at the top. This hand wheel and lead screw is for coarse adjustment of the spindle height. The screw is approximately 28 centimeters in length, so that's roughly how much travel the spindle has. Now, this is only for coarse adjustment because it needs to be locked down. If it's not locked down, there is a lot of play on the column. This knob here locks it down, and then that makes it a lot more stable. You have to remember to always unlock it if you want to adjust. Just lower the spindle a little bit. It lowers quite easily. However, for raising it, it's a little bit more of a slog because you're raising the weight with a rather small screw. I find what helps is to give it a little bit of a pressure underneath, and that makes raising this motor head a lot easier. Okay, let's lock this down and turn to how do we adjust the spindle in smaller steps once the coarse adjustment has been set. To do this, we need this little apparatus here, a fine feed mechanism, which extremely annoyingly Proxxon does not include as a standard equipment. You gotta buy it as an accessory, and it's a little bit expensive. You absolutely need it. It is not optional. Now, what this fine feed does is, just as the name would suggest, it allows you to adjust the spindle height in very fine increments. And now that the system is locked down, at least hypothetically, it would be better for actually milling metal. If you were to try milling metal with this thing unlocked, well, it's going to rattle around like crazy. However, the spindle the quill should be locked well with this knob, and that eliminates any sort of play in the spindle, or at least hypothetically. Without this lockdown, we can see that there's a little bit of play there. Now, that is for fine adjustment. You can also use it as a drill by deactivating or disengaging the fine feed mechanism, and now we have a standard drill press type of operation. The stroke length that is available is about 32 millimeters. Now that mostly accounts for all of the Z-axis controls. Just a little bit of usage notes. Proxxon does recommend that you add a drop of oil to the quill every time you use it, and add a drop of oil to this lead screw. Seems like a good practice to me. I also find that the oil that you add to the quill, it does tend to eventually accumulate at the bottom of the quill, and, well, not a bad idea to wipe the schmoo away occasionally as well. Now, there is one final control. I almost forgot about it, but I just remembered. There is a set screw right here, and what this set screw allows you to do is you can loosen it, and now the spindle's angle can be adjusted at least in one axis, and you can lock that down. I really never use that functionality, however. Main reason why is that there is no way to do fine adjustment. Even the gradations are only in 5-degree increments, and your mileage may vary. Anyways, that finishes up a look at the controls and the basic usage of the Z-axis of this little machine. Let's proceed with the decapitation. That can be lifted off like so. Now let's remove this lead screw from the column block. Note to self, clean this a little bit more frequently. So here we see the Z-axis course adjustment disarticulated from the specimen, and clearly there are some similarities in the pedigree between this and the table. The hand wheels have the similar sort of aluminum. There is that steel, very nice and smooth knob, just like on the table. What's a little bit different, however, is rather than an engraved aluminum scale, it has a plastic scale. This aluminum scale is 1.5 millimeters per rotation. This is only 1 millimeter per rotation. 8 millimeter diameter shaft, 1 millimeter pitch, and it's reverse threaded. Otherwise, some similarity. Another difference is that the end block of the table is made out of steel, while this end block is just made out of aluminum. Here's the end block up close. That's just a washer. Notice that there's no bushing in there. It'd be nice if it was steel, but I guess that's expensive. Now the bolt that tightens the quill block onto the column block also happens to be the only fastener that's holding this column block and quill block together. Well, here we see it. It's a fairly large chunk of aluminum that's being, well, cast mostly, but machined where it's important. There is the hole through which the lead screw feeds, and that hole, by my estimation, it's threaded about 1 centimeter from the top side. The bottom side's a smooth bore. This is the main bore that slides onto the column, and then there's a keyway that keeps it more or less straight. And if you got a keen eye, you might notice that hole is not standard. That's something I did, and I'll explain that a little bit later on in the video as to what that purpose is. Some slots are milled through as well. That's going to help with allowing this to be clamped on. Okay, let's remove the fine feed. It's held on by a single screw, like so, and that just pops off like that. Fine feed, black, and I don't think it's not steel, it's just aluminum. And a little bit of schmoo there. So this here would be the shaft that is going to interface with the quill lever. So when you turn this, it very gradually rotates that interface shaft. It's not entirely clear to me what sort of maintenance this part would need. That seems to be press fit. That pin, I don't think that's removable. I guess it just needs lots of regular oiling. A bit there and a bit there occasionally. I suppose. And from this angle we can see how the quill is fed. I'm going to feed it a little bit and turn it to the camera. Here is the rack on the quill. And one thing I'm a little bit concerned about is that swarf can build up on that rack and then get slurped up and be meshed between that rack and the pinion. It might cause a little bit of wear over time. Let's take it apart and see whether that is really the case or not. This set screw holds the quill feed in place. It's just a retaining screw. A little bit of an annoying screw because if you tighten it all the way down, it locks up the quill feed, so you need to back it off a touch. However, it's really loosey-goosey in there, and I find over time this set screw tends to work its way out. And that's problematic, because if that happens and the quill falls off, I really got to get to Loctiting that down someday. Anyways, let's pull off the pinion and see what sort of condition it's in. Well, it's pretty gooey, pretty schmooey. The good news is I'm not seeing a whole heck of a lot of swarf on there. Well, here is the slot, and that slot is going to interface with this fine feed mechanism, like so. So that's how the fine feed mechanism works. Let's put this aside, and let's now take this the quill block right off. Now to do that, there's a set screw here and there's a set screw here, and what those set screws do is they act as a guide for the quill block to guide along the quill, and they also interface with the spring that's inside the quill that gives a spring return mechanism. There's one set screw out. Yeah, let's get the other one. Turning. Ooh. You see now that the set screws are being removed. It's no longer interfacing with the spring, which is inside the quill. Here is the quill block in its full glory, full gooey, schmooey glory. And we can see that here's the bore for the quill. Here's the quill lock, and the quill lock, what it does is it pinches down on the bottom front part of the quill block, and that's going to pinch the quill and hold it steady. Here is the part that will fit into the column block, like so. Now, I did a modification on the column block. I made a M5 threaded hole right there. Another small modification I did is on the quill block, I milled a flat on that part right there. Explain it later. Anyways, that is the Z-axis in its full glory. So now let's put it back together and test it out. The Z-axis fits back together really easy peasy, so we're ready to now run some tests. Let's begin with tramming the mill in the X-axis. Well, it's not really tramming because that would imply some degree of precision, and since there's no fine adjustment, the best we can do is hopefully get it a little bit more perpendicular than it is at the moment. Ordinarily, I would square it off of a rod stuck in the spindle. However, that would imply that this mill has low runout. And, well, spoiler alert for next video, it doesn't have low runout. So I'm going to square it based on the quill. The quill, by the way, it's made out of steel. I'm not sure whether I mentioned that previously. So the first thing we need to do is get the height, rough height adjusted approximately. I already did that. Make sure that the quill block is locked down. Make sure that the column block is locked down. And stick a hex key into that adjustment screw here on the side. There it is. And loosen it up a little bit. And now we can adjust this straightness. I'm going to add just a little bit of tension. There we go. And to square it up, I'm just going to use a square and slide the square up to the quill. And I find if you rock back and forth a little bit, you can get a reasonable feel as to where it is perfectly square. And let's try that again. That's about right there. Okay, so I tightened it down. Hopefully that is square. Well, let's give it a test and see whether it actually is or not. A dial indicator, a test indicator here. And let's set it up to check this mill in the X. I have it now set up at the bottom of the quill. Use the table to zero it. And there we go. So what I'm going to do is I'm going to loosen up the column block. I'm going to lower the motor head down about 3 centimeters and see how much drift happens on this z-axis. Now, to keep things roughly comparable, there is a little bit of a wobble. I'm going to loosen up the column block at the moment. There is a bit of wobble here, so every time I tighten it down, the wobble's because the key and the keyways is a little bit of some tolerances there. Every time I tighten it down, I'm going to push the motor head to the right. So let me lower it now about 3 centimeters. There we go. And I press it all the way to the right. And I'll lock it up. And it seems that it is about 5/100ths of a millimeter off over 3 centimeters. Not terrible, not great. Let's see if it's repeatable. Loosen it up. I'm going to raise it back up 3 centimeters to how it was. Push it in. Tighten up the column block. And it returned more or less to where it started off by about 1/100th of a millimeter. That's, again, a little bit of the wobble in the column block from locking it down and unlocking it and locking it back down. Remember, it's just a rough adjustment. Okay, well, that is in the x-axis. Now let's check out the y-axis, which a bit of a preview. It's going to be horrific because the y-axis has absolutely no adjustment. Now we're ready to do the y, and there is no adjustment for the y, and it's not square whatsoever. I'm not going to even bother getting the test indicator out, and I use this precision protractor, thank you eBay, to get a handle as to exactly what sort of angle this quill is off by. I'll pull it in nice and tight like so. There we go. Uh-oh. I need to get the magnifying glass out. And that is off by about 15 minutes of arc. Terrible. Well, there is no adjustment. However, I did figure out a way to help correct this problem a little bit. Do you remember that hole that I drilled and tapped? Do you remember that flat? That screw goes in that hole. It impinges upon that that back end of the quill block, and what it's going to do is help prevent this mill from basically its nodding toward the column. Okay, good and snug. Now let's try measuring it again. About like that. And how is it improved? A little bit. We are now down to about 10 minutes of arc instead of 15. Now, unfortunately, that's about as erect as this mill is going to get in the y-axis. I'm not sure what else could be done. I had the idea of maybe putting some screws in here that can push the quill block up a little bit further. However, that'd be problematic as there's a big fastener that goes through, there's slits in there, so I'm not sure what else could be done. However, I do believe that my modification helps a little bit, and I think it'll also help with stabilizing the juncture between the quill block and the column block, and that'd be beneficial for milling in general anyway. Let's test the accuracy of the fine feed mechanism, not the precision. The precision is 1/20th of a millimeter. That means that there's a tick mark every 0.05 millimeters. Accuracy is whether that 0.05 millimeters per tick actually translates into reality. That will check with a dial indicator. Why I'm a little bit suspicious about that is because there's a number of linkages between this wheel and the quill. You got a worm gear in there connected to a spur gear and a rather coarse rack. So let's give this a whirl. I'm going to start off with setting this to 0, and then I'm going to set the dial indicator to 0. Okay, that's pretty good. Now, let's start feeding the quill. Let's go, first of all, 1 millimeter. 1 millimeter, and we can see that it's actually a little bit shy in reality. It's, instead of 1 millimeter, it's about 0.97 of a millimeter. Now, let's keep feeding this. We'll do maybe 10 millimeters. Okay, so there's 1.5. There's 3. And 9.5. And then finally 10 millimeters. And at 10 millimeters, we are out by about 0.3 of a millimeter. So for every 10 millimeters of quill feed with this fine feed mechanism, it's actually only advancing 9 millimeters, 0.7 some odd. So you wouldn't be able to rely on this dial for critical depth adjustment. Now let's test rigidity in the X-axis. I have the quill retracted, the quill is locked, the column is locked, and we are testing on a ground rod that I've stuck in the collet, tightened up good. The collet is at about 10 centimeters height from the table, and where I'm measuring from is at about 5 centimeters. Now to put on a horizontal load, I have a little spring scale graduated in kilograms, and let's add 4 kilograms of X-axis load, 3 kilograms, 4 kilograms, and we're getting about 11/100ths of a millimeter in deflection. Once I release the tension, it returns largely to 0, not entirely to 0. There's probably a little bit of play in the column block, possibly in the quill block as well. Now let's test it in the y-axis, which will be a little bit more interesting. Same setup in the y-axis, and I give it about 4 kilograms of load. And once again, around 10 or 11/100ths of a millimeter of deflection, and returns to 0. So I loosened up my screw modification. Notice that the mill's nodding a little bit further. Let me zero this and put it under 4 kilograms of load once again. Pick up the scale. 4 kilograms incoming. 2, 3, 4 kilograms, and now it looks like closer to around 11 or 12/100ths of a millimeter deflection. So it does seem that my screw does help out a little bit with rigidifying the mill. Okay, now let's run some further tests and see if we can figure out where exactly in the system the flexure is originating from. I'm going to start by testing further up on this ground rod close to the spindle. Next, I'm going to test the spindle itself and see whether there's any flexing between the rod and the collet and the spindle itself. Next, I'll test the quill block and see whether there's any flexure between the spindle in the quill relative to the quill block. And then lastly, I'm going to put the test indicator on the column and see whether this column itself is flexing at all. I've seen on the internet some comments saying, oh, fill the column up with concrete, make it more rigid. I'm not really sure that the column is actually what's contributing to the flexing that we measured a little bit earlier. I suspect it's somewhere else. Well, let's figure it out. I retightened my quill block locking screw, my modification, And now I'm testing much closer to the spindle at about 10 centimeters of height. Back down at 5 centimeters of height, we had about 10/100ths of a millimeter of deflection at 4 kilograms. Let's add 4 kilograms now. And we are getting about 5/100ths of a millimeter of deflection. That really does show you that you got to use as short of a bit as possible to reduce chatter and make it a little bit more stable. Okay, now we're on the spindle itself, or at least the spindle nut. Let's add 4 kilograms of load. And we can see that deflection now is down to about 3/100ths of a millimeter, which suggests that there's a little bit of flexing going on between the rod and the spindle. These collets, next video, I don't really like them very much. Okay, now we're measuring the quill block, adding 2, 3, 4 kilograms of load, and notice that the deflection is only about 1/100th of a millimeter. That suggests that there is a lot of flexing going on between the spindle and the quill block. Interesting. Now let's test the steel column. And I give it 1, 2, 3, 4 kilograms of load, and the needle is barely deflecting at all. Let's give it 5 kilograms of load. A reef on it. I'm giving it maybe 10 kilograms of load now, and we're getting 1/100th of a millimeter of deflection at the most. Yeah, filling this column with epoxy or concrete or something like that, I ain't going to do jack all. Well, that completes our look-see at the Proxxon FF230, or at least the Z-axis thereof. Yeah, it's a little bit of a wobbly mill. It is rigid enough to work with stainless steel or steel. You can check out some of my videos on my channel. I got some projects there that show you what this mill can do. It'll eat carbide bits faster than China Post can provide the new ones to you, and that gets expensive really quick. One thing that I have had some luck with are these indexed carbide bits. The indexed carbide means that it has a steel shaft, and the steel shaft, well, it helps absorb a little bit of the vibration inherent in the mill. I know you're probably interested in what they are. You can find them on eBay. And there is the part number for them. Yeah, I like this mill nonetheless. There are some places where it could be improved. I figured out that a screw being added to the column block in this location does help rigidify and improve the anglage on the quill block. And in doing this video, I think I figured something out. And what I figured out is that there is a bit of play between the quill and the quill block, and that makes sense because when you tighten up the quill block, you're tightening up at the bottom. At the top, there is no tightening going on, so the quill has a little bit of wobble in this quill block up at the top. Now, a potential fix, and one that I'm going to try sooner or later, is drilling a hole in the quill block at an angle like this and threading it and putting a nylon tipped grub screw in there, and that way I can tighten down the quill at both locations for any sort of critical milling sort of operation. Anyways, thanks for watching, take care, and next time I will take a look at the spindle and the power head.